Hello again and welcome to what I hope to be is a quick but an important video on defining the initial concept of electric potential energy, electric potential, two similar but different words, and potential difference, commonly called voltage. The objectives of this video lesson will be to understand how work is done on a system of charges to increase the system's electric potential energy, which we'll call U sub elect. 2, to define the concept of electric potential, and to define the concept of potential difference. So let's go ahead and get started. Because we're somewhat pretty familiar and pretty competent with the idea of mechanical energy, lifting masses above the earth and gaining potential energy, gravitational potential energy, we're going to start with that idea. So look over here, and if I were to grab one of these masses, if I were to grab one of these masses and lift it from the surface of the earth to some distance above the earth, obviously that would take work. I'd have to exert the force over that distance above the earth. Force times distance is work. And when we were done, we would store that energy as potential energy, mgh. Similarly, if I take the large mass and do the same thing, lift it to the same height above the earth, it took more work, it was more massive, I had to exert greater force, but it was the same distance. I would store energy, and I would call that big M, GH, for potential energy. Now this is going to kind of sound weird, but at that region in space, that red ring around there, the same height above the Earth, that region has the potential to produce gravitational potential energy. The only thing I need to do to realize that potential is to put a mass at that location in space. So at any location in space on this red ring, I have the same potential to produce potential energy. And how would we talk about that? Well, if all I need to do is bring a mass in there, then the potential might be talked about in terms of joules per kilogram. If I were to bring a mass up here, a large mass, I would have more gravitational potential energy. If I bring a small mass, I have less gravitational potential energy. So that ratio is going to be an important idea when we get to charge. Basically, if we take the energy, and for gravity, we divide it by the mass, little m divided by little m cancels, big M divided by big M cancels, we get the same ratio. We get just G over H. And that could define something really useful to us. That could define something we call the gravitational potential. Not the gravitational potential energy, the gravitational potential. So any point in space at distance h away from the surface of the Earth, like on this ring, has the same potential to produce potential energy. All we need to do is put a mass in there. So really we could find gravitational potential, U sub G, by taking that potential, GH, and just multiplying it by the mass that we put in there. And that gives us the old gravitational potential energy equation. Let's see how similar two charges are to two masses. So I've chosen to use a system of positive charges, but it would work for negatives and positives as well. Here is, instead of a gravitational field, we have an electric field, which is represented by these vectors here. The electric field has some strength that we're defining at some point in space, and that's the distance from the large positive charge, this guy, at the red ring around there, the same distance around there, trying to recenter that. So just as it takes energy or it takes work to push a mass up high above the Earth, two positives want to repel. So it would actually take energy or work to push these two charges together. I'd have to push with the force some distance. It would take more work to push that big charge, because by Coulomb's law they repel stronger, so I'd have to push harder to get them close together. But I would also have to push this little charge a certain distance and bring them to the same distance away from that positive charge. It would take less work. But again, on that red ring around that charge, that one space around the charge, that space has potential to produce electric potential energy. So remember what we just said with the gravity example. if we take that gravitational potential, which we said was just GH, and the units of that would be joules per kilogram, and we multiply it by the mass, we get joules. So in this case, we're going to define electric potential energy, U elect, and instead of a mass, we have to bring a charge near the other charge, or a charge in the electric field, so that's Q. And we're going to introduce a new term, but a term that you've heard. Instead of GH, which does not apply to charges, we talk about electric potential, and that is capital V. You might guess what the V stands for. The V stands for electric potential, and the units of electric potential is a joule, and instead of a joule per kilogram like we use with gravity, it would be a joule per coulomb. And we have a shorthand way of saying that 1 joule per coulomb, per single coulomb, we call 1 volt. So that's where we see that commonly used word. A lot of misconceptions with what it means. A volt is not the same as energy, although it's related. We're going to discuss a little bit more what's voltage when we use it in everyday language. But in this case, electric potential is the potential to produce electric potential energy. It's a mouthful, but it's true. So this would be our equation to actually calculate in joules how much electric potential energy is there a system in charges. The electric potential is produced by that big charge, and if we bring a little charge inside in the electric field of the big charge, then we can calculate how much energy the system has. So if you remember when we did study mechanical energy, we didn't spend very much time just dealing with what is the absolute potential energy of a mass some distance above the Earth, because it really wasn't that useful. What was far more useful were changes in potential energy. And by that I mean if we want to study what's going to happen to a mass at the top of the hill, just knowing its energy at the top of the hill is not super useful. But knowing how its energy would change going down the hill is useful. We could then predict how much of that energy is converted into kinetic energy. We're going to do the same thing with charge, except we're going to look at it kind of like the way we look at a topographic map, which you might be familiar with. So here's the analogy here. We're looking at a two-dimensional landform, and we're going to then plot on a two-dimensional surface here, a flat surface, the contours of it. So this would represent this region right here, 40 meters above sea level. This would represent 30 meters above sea level. So if I walk on these contour lines, sometimes they're also called isoclines, I don't go up and I don't go down, I stay at the same elevation. So if I'm interested in what's going to happen going from high to low, really what I want to know is how do I go across those in order to convert high potential energy to low potential energy. What we have over here is not a landform, but sort of like a landform produced by charges. So here's Q1, here's Q2, and here's Q3. And just as this region, right, we could define its potential just by saying GH, G being the acceleration of gravity, H being 20, we know the potential energy of something if we just know the mass at that location. The same thing is here. So these contours are constant electric potentials, and they would be measured, in this case, that contour is 5 volts. Down here in sort of what looks like a geographic valley is 0 volts. So just as if I want to know how a ball is going to convert its gravitational potential energy to kinetic, if I put a charge somewhere in this landform, so to speak, it's going to flow from high potential to low electric potential. And it's that difference really that's important, because once we get the charge to move from high potential to low potential, that's current, electric current, and electric current is super useful in our modern world. So really what we're more concerned with is potential difference, and that's what we call voltage, is a difference. So in physics we usually use delta capital V for that. Just to give you an idea of where you see this all the time, a battery, AA battery, might be 1.5 volts. And what they actually mean is the potential difference between the two terminals of the battery. This might be 0 volts. This would be 1.5 volts. the difference is 1.5 volts. So if I provide a circuit, a path for charge to go from high to low potential, I can use that moving charge or that current to do work for me, and that's really useful in our modern world. These are concepts that we're just touching on right now. We're going to practice over the coming days in class, but having an idea of what voltage is, how it relates to electric potential energy is essential for moving on. So do the Google form, submit your homework, and when we get together in class, we're going to work with these concepts more.